Hi everyone! Today let's talk about Chapter 3, Probability, Section 3.1, Sample Space and Event. Definition: Sample space S is the set of all possible outcomes of an experiment. Its elements are sample points, and we can also call outcomes. Its subsets are called events. Okay, so the set of all possible outcomes are called the sample space, and the outcomes are called sample points or outcomes. We usually just call outcomes, and then the subsets are called events. So last time we talked about the empty set is the set with no elements. And we talk about the union, so it looks like a U, right? Union is like A or B. It's the set containing all the elements. Those are either in A or B or both. A intersects B, so this is the intersect. Think about and. A and B, okay? So A intersects B is the set containing all elements. Those are in both A and B. And we also talk about the set minus. A set minus B is the set of elements. Those are in A but not in B. So you start with the elements in A and then you look at the B. Well, you take out the elements which is in B, okay? And then the complements of A is the universal set. Sometimes we call the universal set the U, or we can use S for the sample space, okay? And this is a set. It's a subset of S that contains all the elements of S. Those are not in A. Today, let's draw a Venn diagram. Okay, so let's draw a Venn diagram. So S is the universal set, and A is a subset of S. So we can draw it like this. So A is a subset of S. And then the complement, what is the complement? So if this is the A, complement is outside of A. So all the elements outside of A. So this is A complement. A complement is also a subset of S. And notice that A intersect A complement is empty because complements of A and A, they don't have common elements, so the intersection is empty. And A union A complement is actually the universal set. And if we have two sets, A and B, so this is A, this is B, what is the union? So A union B is like everything in A or in B, so A or B. Alright, and how about intercession? So A and B is this piece is the common region. Okay, let's draw more. So how about this guy, A, B? How about this piece? Notice that this piece is in A but not in B, so we can use A minus B. And it's also, because it's in A, so it's in A and not in B. Not in B means it's in the complement of B, right? And let's see. So this is A, this B, then what is this region? This region is in B, but not in A, so it's like B set minus of A. And it's in B, but not in A. Not in A means it's in the complement of A. And then do you realize that A union B is the union of A intersect B and A intersect B complement and B intersect A complement. And all these three regions, they are disjoints. Disjoint means they don't have common elements. Their intersection of two of them is empty. Okay, so they are all disjoints. Alright, let's continue. Example 1. If A is the event that a certain student is taking a course in calculus, B is the event that a certain student is taking a course in physics, C is the event that a certain student is taking a course in chemistry. Express in words what events are represented by the following regions. Region 2. So region 2 is right here. Do you see it's in A, it's in C, but it's not in B. So A is calculus, B is physics, C is chemistry. It's in A, so students take what? It's in A, so take calculus. Is in C, so take chemistry, but not physics. Okay. Region 1 and 3. So 1 and 3, let's see. Alright, so 1 and 3, you can see students take, so it's in B and in C. So students take B is physics. And in C chemistry. Well, you might notice that, okay, how about A? We didn't mention A. Actually, we don't need to mention A because you can see region 1. Region 1 are the students take B and C and A. And region 3 is in B and C but not in A. So when we combine them, we have students, some of them take calculus, some of them don't take calculus. So you don't have to mention about calculus. This piece, the blue region, is just B and C. Okay, how about I also use notation? So B and C. So region 2 is in A and in C, but not in B. Not in B means in B complement. And then next. Okay, region 3, 5, 6, 8. 3 here. 5, 6, 8. Oh, what happened? It is the complement of A. So these are the students do not take calculus. So far, so good, everyone. Okay, so this is the Venn diagram, and we can look at the informations to find the answers. Okay, let's continue. And that's it for 3.1. Let's continue. 3.2, counting. We have the fundamental counting principle. If the sets A1, A2, AK contains respectively N1, N2, NK elements. So there are N1 times N2 times NK ways of choosing first elements of A1, then an elements of A2, and finally an elements of AK. So for counting, you want to ask questions. Can we divide the activities into steps? Okay, so if we can divide the activity into steps, then we multiply them. Okay, and if we can divide the activity into cases, then we add them. Alright, so let's look at example 1. In how many ways can a union local with 25 members choosing a vice president and a president? So here we want to choose a vice president and a president. So you can separate into steps. So step 1, we choose a vice president. How many ways are there? Well, we have 25 ways, right? There are 25 members, so 25 choices. Then step 2, we want to choose a president. So because we already choose one member, then there are only 24 members left in the second set. So that's why we multiply by 24. So 25 times 24, what is that? So 25 times 24, 600. So there are 600 different ways. And you can see step 1 and step 2, we can switch the order, but the numbers will be the same. So maybe the first step you can choose a president, and in the second step you choose a vice president. So far so good. So here we can, if we can separate into steps, then we multiply them. We multiply the numbers in each step. Okay? If we can divide an activity into cases, for example, maybe we want to, so maybe in the library we have maybe my personal library, we have 50 math books. Okay, maybe, so let's say in a bookshelf, if we have 50 math books and 20 chemistry books and maybe 17 physics books. Okay, so if part A, if we want to pick one book, what happened? Well, then you separate into cases, because we could pick math book, then there are 50 choice. We can pick chemistry books, so there are 20 choice. Or we could pick physics books, then there are 17 choices. So then when we add them up, we get 87 choices. So this is, we pick a book. We can divide into cases. Okay? That's why we add them. And if we want to pick one math book and one chemistry book and one physics book, then we can separate into steps. Right? We can consider, okay, we first pick a math book, but there are 50 choice. Okay, and then we pick a chemistry book, so there are 20 choice. And then we pick a physics book, so there are 17 choices. So we multiply them together, and what is that? 50 times 20 times 17,000. You can see that part A and part B is, they're quite different. Okay, now you can see the difference between cases and steps. Okay. Example 2. If a test consists of 12 true or false questions, in how many ways can a student mark the test paper with one answer to each question? Okay, let's see. So it has 12 true or false questions, and each true or false questions, there are two choices, either true or false, right? So we can separate into steps. Step 1, okay, so maybe the first question, how many choices? 2 true or false, right? And then second question, 2 choices, Third question, 2 choices. And this is the 12 questions also too. And you know there are 12 copies of 2 multiplying together. So what is that? So 2 to the 12, 4096. So this is the answer. Okay, we have 4096 possibilities. Alright, let's continue. Definition. If R objects are chosen from a set of n distinct objects, any particular arrangement or order of those objects is called a permutation. For example, 4123 is a permutation of the first 4 positive numbers. So the first 4 positive numbers are 1, 2, 3, 4. By the way, if we use set notation, set, the elements in a set, they don't repeat. So you cannot put a 1, 1 in a set. That's not allowed. And the order of elements in the set does not matter. So this guy is the same as 2, 3, 4, 1. So that the order does not matter for sets. Okay, so that's why if you want to care about the order, you use permutation. Okay, so permutation is like a specific arrangement or order of the objects. So, and sometimes people use like the points to denote. Okay, we can also use this point notation because this coordinate notation is like an order list of numbers. Okay. All right, look at the theorem. The theorem is the number of permutations of R objects selected from a set of n objects, if the orders matter, is permutation and choose R. So this is notation. Permutation and choose R. It is, so it's like we have some boxes. Okay, look at the first box. So we want to select R objects from a set of n objects. So here we have R boxes. This is the first boxes, second boxes. This is R boxes. Then the first boxes, how many choices there are there? So we have n possibilities. And then the second boxes, because we already picked 1, now we have n minus 1 possibilities. And then continue. What is the last one? What is the last one? The last one is actually n minus r plus 1. Why is that? Well, you think about it, find the pattern. N is like n minus 0. Now look at this. 1 corresponds to 0, 2 corresponds to 1, then the r corresponds to r minus 1. But there is a parentheses. When you distribute the parentheses, you get n minus r plus 1. So that's why you get this formula. Okay? And furthermore, if you multiply the numerator and the denominator by n minus r factorial. So what is factorial? Okay, factorial. Zero factorial is defined to be 1. 1 factorial is 1. 2 factorial is 2 times 1. It's simply n factorial. It's gonna be n times n minus 1. So multiply all the numbers that are smaller or equal to n, and they're positive integers. Okay, so now after we multiply n minus r factorial in the numerator and denominator, now look at the numerator. The numerator are actually n factorial. So that we get a nice formula n factorial over n minus r factorial. So this is the number of permutation. So far so good, everyone. Okay, come back to our first example. Okay, In how many ways can a union local with 25 members choose a vice president and a president? So because the order matter, right? So that's why you can think of this guy as permutation 25 choose 2. And 25 choose 2, we start with 25 and we times, we count down the number. The next number is 24. So there are 2 numbers together. So this is permutation 25 choose 2. Okay, let's continue. Now, if we want to find the number of ways in which our object is selected from a set of n objects, but we do not care about the order in which the selection is made, we call this set of R objects as a combination. So for combination, the order does not matter. Okay? And think about the let's say the combination. So the combination of the first, so this is a combination, right? And let's see, so these combinations, how many permutations corresponds to these combinations? Well, if we arrange those 4 numbers, how many different permutations are there? Well, we have 4 numbers. The first one we have 4 choices. And then the second one we have 3 choices. And then 2 choices, 1. We have 24. So we have 24, which is 4 factorial, permutations represent the same combination. Right? In general, there are R factorial permutations of any R objects, okay? And they represent one combination, okay? So there are R objects, R factorial permutations of R objects we select from a set of n distinct objects. So we have permutation n choose R. Permutations of R objects contains each set of R objects, R factorial times. So if we want to count the number of combinations, we first look at the permutations. So we have n objects and we want to choose R objects. So there are permutation n choose R, that many permutations. And then we think about how many permutations represent the same combinations. So because we have R objects, so then we have R factorial permutations represent the same combination. So that's why the number of combinations of R objects selected from a set of n objects where order does not matter equals combination n choose R. So this is another notation, parentheses, n choose R. Notice that don't put the line here. The line means this is a fraction. This is not a fraction. Some of my previous students draw the horizontal line there. So that's a fraction, but so this notation, don't put a line there. So this is the number of permutations n choose R divided by R factorial. Okay? And what is permutation n choose R? Remember this n, and then we count down until we have R numbers multiplies together, and then we use it to divide it by R factorial. So it also equals this. Okay, so that is combination. Let's look at some example. So example 3, there are 9 cards in a race. In how many different ways can they place first, second, and third? Well, first, second, and third, order matters. You see, order matters. So if order matters, we use permutation. If order does not matter, we use combination. So keep these in mind. So we have the first place, second place, and third. Oops. Okay, so we can draw boxes. First box, how many choices? 9 cards. Second box, we have 8, and then here we have 7. So 9 times 8 times 7, what is that? $504. Okay, so this is the number of ways that those 9 cards can be placed first, second, and third. Okay, example 4. A carton of 12 rechargeable batteries contains one that is defective. In how many ways can an inspector choose 3 of the batteries and get one that is defective? Part B, not get the one that is defective. Okay, let's see. Here we have, so we want to choose 3 batteries. Get the one that is defective. So we have 3 batteries, and one of them is defective, and 2 of them is not defective. Okay, the order does not matter, right? So here we have the total 12 rechargeable batteries that has 1 is defective. So that's why here defective one, there's only one choice. And here we have 11 not defective batteries. And we want to pick 2 of them. So that's why we have 11, choose 2. And 11, so this is combination 11, choose 2. So 11 we count down, that's 10. And then divided by 2. This is 5, so 55. This is part A. Okay, and part B. Not getting the one that is defective. Okay, so now not getting the one that is defective, which means all of them are not defective. Well, the order does not matter, right? And then, so we just have 11 not defective. We want to choose 3 of them. And then how do we do this? 11, count down, 10, 9. So 3 numbers, stop right here. And then the denominator, we have 3 factorial, which is 3, 2, 1. So 3, 9 cancel, we get 3 on top. Here we cancel, we get 5. So the answer is, let's see. So we have 11 times 5 times 3. 165. So 165 is the answer. Okay, let me change this problem a little bit. Okay, how about we have 12 batteries and 3 of them are defective. Okay, please pause this video and try to complete this problem. Okay, answer also part A and part B. Have you finished? Let's check our work together. So, part A, get one. Okay, get one. Get one that's defective. So here, one of them is defective. The other 2 not defective. Okay, here we have 3 defective. So 3 choose 1 times. Here we have 9 that are not defective because the total is 12. 12 minus 3 is 9. So 9 not defective, and we pick 2 of them. So 3 choose 1 is 3. By the way, let me teach you. So we know. Okay, and let's see. Okay, and choose 0 is the same as n choose n. That is 1. And choose 1 is like n choose n minus 1, which is n. And in general, n choose r is the same as n choose n minus r. Okay, so this is the properties of combinations. So 9 choose 2. What is 9 choose 2? Well, we start with 9 and we count down to 8 divided by 2. They cancel. So 3 times 9, 27. Let's see, 27 times 4. What is that? 108. So this is part A. Now how about part B? Now get the one that is defective. Okay, so all 3 of them are not defective. Then we have not defective, none of them are not defective, and we choose 3. So 9, 8, 7 over 3, 2. Okay, 3, 3 cancel, 3 cancel. So 3 times 4, 12. 12 times 7. 84. Okay, so this is part B. Do you have the same answers? Okay, so let's do more exercise. Let's go back to our previous example. Do you remember this, like the bookshelf example? Oh, okay. Let's see. Let's extend this problem here. Okay, now if I want to ask, we want to pick 3 math books, 2 chemistry books, and let's say we want to pick 5 physics books. What happened? Well, how many math books? 50. We choose 3. And you can see the order does not matter, so we use combination. And let's see, we have 20 chemistry book, we want to pick 2, and we have 17 physics book, we want to pick 5. Okay, so you can continue to, let's see, okay, 50 times 49 times 48 divided by 3, 2, 20 times 19 over 2, 17, 16, 15, 14, 13, 5 numbers, right? Over 5, 4, 3, 2, 1. Okay, so you can plug this in your calculator and check out what it is. Okay, and what if they want to pick less than 2 math books? Okay, let's see. Okay, let's say we want to pick okay, let me think about it. 2, okay, let's pick, okay, 2 math books. Let's see, 2 math books and 3 chemistry or physics books. How do we do this? So we need to have 2 math books, so that's 50. Choose 2. 3, then it's either chemistry or physics. So what do is chemistry we have 20, we add the physics 17. Okay, we want to pick 3 of them. So that's why we have 50 choose 2 and times 37 choose 3. Okay, so you can continue and figure out what this number is. And if the number is so big, you can actually use your calculator, the combination and permutation function, to figure out what the number is. But in the exam, please show all your work. So show all of your work. Okay, don't just give me a number. So if you don't write any explanations, you don't receive points. So be careful with that. So on the so let's see, on our website. So if you go here, combinations, how to use your calculator. Okay, So let's look at this together. This is a video how to show you how to use combinations.
Hi everyone. So right now I want to teach you how to use your calculator to calculate combination. For example, if we have a hypergeometric distribution with the total number is 72 and like the number of green balls is 28, and we pick 10 out of them, okay? So what is the number of blue balls? Well, that's the total number of balls, 72 minus 28, which is 44. What is the probability that the 10 balls we pick, we get 3 of them is green? So that is 28 choose 3. So all of these are combination. 28 choose 3 times 44 blue balls, we choose 7. And then 72 balls, we choose 10. Okay, so how do we put this in our calculator? So this is the calculator I use. So first of all, I need to put parentheses and 28. So 28, and you see I have this probability, and then I can choose combination. So NCR is combination. So 28 choose 3. So we plug in 3 here, and then parentheses. Okay, another parentheses, 44 combination. Choose 7. Okay, close the parentheses. Divided by 72. Choose 10 and close it. So our answer is this. So let me put it down. Okay, so our answer is point.
So from this video, you can see how we type the numbers into our computer and get combinations and permutations, right? So this video also mentioned the hypergeometric distribution, which is in chapter 4, okay? But so you don't have to worry about those knowledge now, but at least this video show you how to type the combinations into your calculator. All right. Okay, very good. So you can use your calculator to figure out these. Okay, I will let you to figure out these. All right, let's continue. Okay, next topic, tree diagram. So example 5, a biomechanical device for medical emergencies can operate for 0, 1, or 2 times a night. Construct a tree diagram to show there are 10 different ways that it can be operated for a total of 6 times over 4 nights. Okay, let's see. So here, let's say each night it operates 0, 1, or 2 times. Okay, let's say M1 is the number in the first night, N2 the number of the second night, N3 the numbers in third night, and then 4 the numbers on the fourth night. Okay, let's construct a tree diagram. So first of all, let's look at the first night. First night, it could be 0, 1, or 2. Right? So let's draw it. So it's like a tree. This is the first line. And then second night, so N2. And second night, it could be 0, 1, and 2. Right? Okay. Think about it, because we want to have 6 times over 4 nights. So if the first night is 0, second is 0, but the remaining, okay, we have 4 bosses, 0, 0. So that the third night and the fourth night, you can at most get 2. But this means the total is 4 times, which is impossible. So we can rule out this case. right? Because we want to have the total of 6 times. And how about this guy? We can have 0, 1. But even though the third line and fourth line we get 2, then the total is still 5. So this is also impossible. Also rule out its cases. And then this means, okay, the first one is 0, and then 2, and we can also have 2 on the third and fourth night. Then the total is 6. So this is good. Okay, so this is one possibility, one way of doing that. Okay, let's continue the tree. Here we have N2. It could be 0, 1, or 2. If it's 0, what happened? 1, 0. Oh, even though we get 2, the maximum is 5. So this is also impossible. Okay, impossible. Let me just rule out, and you know it means impossible, right? And then this guy we have 1, 1, 2, 2. Then we get 6 times. Good. So this is possible. And if this is 2, well, then let's go to the third night. The third night can be 0, 1, 2. Okay, let's look at this. So this tells us that the first night is 1, the second night is 2, third night is 0. So even though we get 2, the maximum is 5. So this is impossible, right? So yeah, we don't get 6 times. And let's see here. This is 1, 2, 1. Okay. If we get 2, this is 6 times. Good. So here, this is good. And we know M4 must be 2. Okay, how about this guy? 1, 2, 2. 1, 2, 2. Then this must be 1 because we want the total to be 6. So M4 must be 1. And this is okay. Alright, let's continue. So we go to N2 and it could be 0, 1, 2. 0, then we can have 2, 0. We can have 2, 2, then the total is 6. So this is good. 2, 1. Okay, 2, 1 we can separate into cases. So let's say M3. M3 we can have 0, 1, 2. These guys we have 2, 1, 0. Even though we get 2, still the total is 5. So it's still not enough. So we can rule out this case. And then here, let's see, 2, 1, 1. And this guy must be 2. So M4 is 2, right? So this is possible. And here, 2, 1, 2. Okay, then this guy must be 1. So M4 is 1. So this is possible. Okay, now let's see. Alright, what is this? 2, 2, 0. Oh, the last one can be 0. Then we have 6 times over 4 nights. Here, 2, 2, 1. Oh, last one could be 1. And this is okay. And then here, 2, 2, 2. Last one could be 0. Okay, M4 is 0, then this is good. Okay, how many are there? We have, let's write it down. So we have this guy, 0, 2, 2, 2. And we have this guy, 1, 1, 2, 2. We have this guy, 1, 2, 1, 2. This guy, 1, 2, 2, 1. This guy, 2, 1, 1, 2. Here, 2, 1, 2, 1. And all 3 of them, 2, 2, 0, 2, 2, 2, 1, 1, 2, 2, 2, 0. How many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9. Did we miss one? Oh, right here. 2, 0, 2, 2. So we have 10 ways. So that 10 different ways that we have a total of 6 times over 4 nights. So this is a tree diagram. You simply look at each steps, how many cases, then you can draw the tree, the branches. So far, so good, everyone. Okay, so if you have any questions, feel free to ask me. Have a nice day. Bye.